All right. As we worked through the exponential distribution and then recently now the gamma distribution, um, we're working with a class of random variables that oftentimes come into play when we think about waiting times. And a lot of times in certain settings, these are being applied to understand survival times or death times of usually of components of machinery and things like that. So this naturally there's a way to deal with these random variables or way to handle them in terms of what are called hazard functions. And so we'll talk about that now. So what a hazard function is a kind of a way to describe a non-negative continuous random variables distribution um, in terms of the so-called survival probabilities. Okay. Which are, as we talked about before, the survival probability is a little different. It's the complement to the cumulative distribution function, which is what we usually use. But when we're talking about positive random variables, these survival probabilities are, in some sense, the more natural. So we're going to let T be a non-negative continuous random variable. With a density F and a distribution function, capital F. And so we think of T as modeling the lifetime of something. And then let's define a function lowercase lambda of T as the probability that T is strictly greater than T, but less than or equal to T plus dt, given that T is greater than T, divided by dt. This is the ratio, 0. So this is the ratio of the probability of dying in the next dt time units given survival divided by the number of divided by the unit of time dt. So it's like the instantaneous this is not a formal statement. It's just it's like the instantaneous time of failure, rate of failure. So the higher this is, the more force there is, in some sense, to die. Okay. Now, lambda t in survival analysis and actuarial science and so on, it's widely used and it's called by a few different names. It's called the death rate, failure rate, hazard rate, at time t. Okay. And S of t, capital S of t, which we define as the probability that t is strictly greater than t, which equals 1 minus the cumulative distribution function of t. This is called the survival probability. Okay. So that's a little terminology. And what we want to look at now is, okay, how can we relate the hazard rate or the failure rate to the survival probability? Okay. Well, let's look at the definition. So here's the definition of the hazard rate. Probability of dying in this instant, given that you're already above t, well, that's just by, you need the probability of both conditions divided by the probability of the condition, but the one condition subsumes the other, so we're left with this divided by dt. Okay. Okay, but then the probability of dying in this next instant in terms of the density is f of t dt. And then the probability of surviving past time t, this is 1 minus the cumulative distribution function times dt. So the dt's cancel, and we're left with ft over 1 minus so we're the density over the survival function. And the density over the survival function, incidentally, is negative of the derivative with respect to t of the log of the survival function. Okay. And so we'll see how that's useful. It's actually quite more useful than you could probably imagine right now. So let's look at an example. Suppose t is exponential lambda. Okay, then the survival function of t is e to the minus lambda t. The density of t is lambda e to the minus lambda t. So then, with that being said, the hazard rate function of t is lambda e to the minus lambda t divided e to the minus lambda t, which is just lambda. It's constant for all t. This is what's called the constant. So in actuarial science, this is called constant force of mortality. But it also is very much tied to the memoryless property, right? It's saying that the hazard rate, the failure rate, does not change with t. So it doesn't matter how long or how short something has lived, the hazard rate stays the same. In general, if we let lambda of t be the hazard function, for a random variable t, it's non-negative, then the integral from 0 to t of the hazard function is equal to the minus log of the survival function from 0 to t, which is equal to minus log of the survival function at t plus the log of the survival function at 0. Now, what's the log of the survival function at 0? Well, the survival function at 0 is 1, because it's the probability that something that's positive is bigger than 0, which is 1. So, and the log of 1 is 0, so this is just 0. So this is minus log ST. Okay. So then what do we have? We have, let's put it down here. That integral 0 to t lambda equals minus log of s of t, which we can invert to get an expression for the survival function as exponential minus integral 0 to t of the hazard function. And the density, which is equal to minus the derivative of the hazard, or of the survival function, is equal to the hazard function times the survival function. Okay. So, couple of consequences that we can see from this. Number one, if lambda t is fixed, is a constant for all t, then the survival function is equal to e to minus rho t, and the density, which is the hazard function times the survival function, these are exactly the density and the survival function of the exponential with parameter rho. So constant hazard gives us exponential. That's guaranteed. And if t is memoryless, then the hazard starts over at every period point in time, meaning that the hazard at any given time t has to equal the density at time 0 for all t. But this means that t is going to be exponential with parameter lambda equal to the value of the density at time 0, and that's exactly what the exponential density is. Okay, so that's a little bit on hazard functions. What makes hazard functions nice if we're in the specific setting, is that we specify the hazard function and we immediately get the density and the survival function for that. And so we have an easy, a straightforward way to describe the distribution. And so it becomes convenient in specific settings. Especially in settings where we're dealing with multiple independent copies of a random variable. In those cases, if we're interested in things like the minimum, as we saw in a previous lecture, then we use independence to our advantage, and the survival function becomes particularly useful in that case. So we'll see another example of a different hazard function in the next lecture.